In this lesson, we'll discuss incidence geometry. Incidence geometry is an elementary part of geometry, and we're going to assume only the following undefined terms: a point, a line, and incident. What it means for a point and a line to be incident. And recall we say that a point lies on line M, or M passes through P, or P is incident with M, or M is incident with P. These are all equivalent statements. Along with these undefined terms, we will also use the following defined terms. We say three or more points, A, B, and C, and so on, are collinear if there exists a line incident with all of them. So all of these points would be lying on the same line. Three or more lines, L, M, N, are concurrent if there exists a point incident with all of them. And it can be shown that this point of incident is unique. So we have three or more lines that intersect at one point. These lines are called concurrent. And our definition of parallel, two lines L and M are parallel if they are distinct and no point is incident with both of them. So the undefined terms will be subjected to three axioms. The first of which is the same as Euclid's first postulate. The first incidence axiom is that for every point P and every point Q not equal to P, there exists a unique line L incident with P and Q. The second incidence axiom says that for every line L, there exist at least two distinct points incidents with L. The third incidence axiom states that there exist three distinct points with the property that no line is incident with all three of them. So now with these incidence axioms, we can assert that every line actually has points lying on it, at least two, possibly more, and that the points do not all lie on one line. From axiom 3, we can conclude that at least 3 points exist in incidence geometry. So we just defined collinear. We could have written incidence axiom 3 as there exist 3 non-collinear points, and then also we have parallel lines still being lines that do not have a point in common. So now with just the restriction of these three axioms, we can try to see what kind of results we can prove. This first proposition is an example of a statement that we can prove using only the incidence axioms. If L and M are distinct lines that are not parallel, then L and M have a unique point in common. So let's look at the proof. So let's assume that L and M are distinct lines that are not parallel. Well, since they're not parallel, by definition of parallel, they must have a point in common. To prove uniqueness, let's suppose to the contrary that L and M have two distinct points, A and B, in common. Now we can use incidence axiom 1, so we have two distinct points, so we can say that these distinct points A and B lie on a unique line. But A and B both lie on lines L and M, so we can conclude that since this is a unique line, that L must equal M. But this contradicted the hypothesis that we started with, that L and M were distinct lines that are not parallel. So this contradiction allows us to conclude that the intersection of L and M is actually unique. And that proves the proposition 2.1. Let's look at some more propositions. Proposition 2.2, there exists three distinct lines that are not concurrent. Proposition 2.3, for every line, there is at least one point not lying on it. Proposition 2.4, for every point, there is at least one line not passing through it. And proposition 2.5, for every point P, there exists at least two lines through P. Whenever we prove a proposition, we can always use a theorem that's already been proven. So in order to prove proposition 2.2, you could use, for example, proposition 2.1. According to the rules of logic, we can build upon previously proved statements. Let's prove one more of these propositions. Proposition 2.2. There exist three distinct lines that are not concurrent. Well, if we look at our incidence axioms, we see that incidence axiom 3 states that there are three distinct points, call them A, B, and C, that are not collinear. So now that we have three distinct points that are not collinear, we can use incidence axiom 1. We have these three lines, AB, AC, and BC. And we claim that these three lines are not concurrent. These lines also must be distinct, otherwise the 3 points would be collinear. Because if AB was equal to AC, then all 3 points would be on the same line, and so on. So we know that these three lines are distinct. Now for a contradiction, let's suppose that these lines are concurrent. Then they intersect at a point D. So there's a point D that is incident with all three lines. Now I'm going to pick one of the points A, and I can use the fact that D either equals A or D does not equal A. And those are going to be my two cases. So first, if the point D is equal to A, then again all 3 points are collinear, which would be a contradiction because D is lying on all three lines, and if D equals A, then all 3 points A, B, and C would be on the same line. So again, D cannot equal A. So the final case is if D does not equal A, then AB and AC do not have a unique point in common. They would have a point A in common and another distinct point D in common, but that contradicts our previous proposition, proposition 2.1, which states that distinct lines that are not parallel have a unique point in common. So we can conclude that there is no point D that's incident with all three lines, and therefore lines AB, AC, and BC are not concurrent. Now that we have the incidence axioms, we can imagine how these axioms would look if we try to represent them with drawing. So if we have any axiom system, we can interpret the undefined terms in some way, in other words, give the undefined terms a particular meaning. We call this an interpretation of the axiom system. So an interpretation of a given axiom system is a way to assign a particular meaning to each undefined term. Here's an example of an incidence geometry called three-point geometry. So consider the set of letters A, B, and C. We're going to define the points of this geometry as the letters A, B, and C. And lines are going to be subsets of the set A, B, C that only contain exactly two letters. So there's going to be three lines, the subset AB, AC, and BC. And incidence is defined as set membership. So for example, A lies on the line AB and AC, but not on the line BC. So this is one interpretation of the incidence axioms. Now, given an interpretation of an axiom system, when the axioms are actually correct statements, we now call that interpretation a model of the axiom system. So in the previous example of three-point geometry, we saw that was an interpretation of incidence geometry. But is this previous example a model of incidence geometry? So we need to check the three axioms. Incidence axiom 1 says if P and Q are distinct points, then there's a unique line through P and Q. If we pick P and Q, which are any two distinct letters in the set ABC, we see there's exactly one line, PQ, which is through P and Q. So axiom 1 is a correct statement. The second axiom we need to check that for every line there exists at least two distinct points incident with that line. If we pick any line in this model, it has exactly 2 points. There is at least 2 points in every line. And the third axiom, we need to check that there are 3 distinct points with no line incident with all 3 of them. And we see that A, B, and C are distinct and they are not collinear. So yes, this 3-point geometry is a model for the incidence axiom system. So why do we use models? What use are they? Well, the main property of a model of an axiom system is that all the theorems of an axiomatic system are correct statements in the model. So by the way we define a model, all the axioms are correct statements. So since theorems are logical consequences of those correct axioms, then we know that theorems also hold in these models. So we can use models as a testing ground to test whether or not an interpreted statement is correct. So we have a statement that we're not sure if it's a theorem or not. We're not sure whether it is a correct statement. We can test it in various models. And if we find one model where the interpreted statement fails, then we know that it is not a theorem. So if we can find just one model when an interpreted statement fails to hold, then the statement can't follow from the axioms, and we can conclude that no proof is possible of that statement. So it's to our advantage to have several models of an axiom system so we can use them as a laboratory to see if statements hold in one model but not the other. So we can use models to explore the parallel properties. Recall the 3 parallel properties. First, the elliptic parallel property, which states that for every line L and for every point P not on L, there exists no line parallel to L passing through P. So the Euclidean parallel property, which states that for every line L and for every point P not on L, there exists exactly one line parallel to L passing through P. And then we have the hyperbolic parallel property. For every line L and every point P not on L, there exists at least 2 lines parallel to L passing through P. So in the elliptic parallel property, we have no lines parallel to line L through P. Euclidean, we have exactly 1, and hyperbolic, we have more than 1. So we can look at models of incidence geometry and see which of these parallel properties hold in a certain model. So here's a drawing of the 3-point geometry, and we want to look at the Euclidean parallel postulate. Is this a correct statement in the 3-point model of incidence geometry? So in this model there are actually no parallel lines. In fact, every pair of lines intersects in this model. So this model has the elliptic parallel property that any 2 lines have a point in common. So we can conclude that no proof of the Euclidean parallel postulate is possible using the incidence axioms alone, because the Euclidean parallel postulate is not a true statement in the 3-point geometry model. And in fact, in incidence geometry, it is impossible to prove that parallel lines exist. In the same way, the statement no parallel lines exist cannot be proved. So although the elliptic parallel property holds in the 3-point geometry model, it doesn't hold in kind of the usual drawing of Euclidean geometry. So we can't use the incidence axioms alone to prove the elliptic parallel property holds either. So statements like parallel lines exist can't be proven, and it can't be disproven. So we have a definition for this type of statement. We say that a statement in the language of the system is independent of the axioms if it is impossible to either prove or disprove a statement using the axioms. So if a statement holds in one model for the axiom system but does not hold in another model of the axiom system, then it's going to be an independent statement. This is how we actually show independence. So to show that a statement is independent, we construct 2 models for the axioms, one in which a statement holds and one in which it does not hold. the example which I just mentioned, parallel lines exist, is independent of the axioms of incidence because it holds in the usual Euclidean model, but it doesn't hold in the three-point geometry model. So when an axiom system has no independent statements, we call that system complete. Every statement in the language can be either proved or disproved from the axioms in a complete axiom system. So we see that the incidence axioms of geometry are incomplete. Now let's consider the following interpretation. We have a sphere, and the points on the sphere are going to be the points in this geometry. Lines are going to be great circles on a sphere. So a great circle is like, you can think of the equator, where it's a circle where the center of the circle is the center of the sphere, and the radius is as big as it can get. It's the same radius as the sphere. Incidence would be line on a great circle. So if a point passes through the great circle, then it's on that line. So when we look at this picture of the sphere, we want to ask ourselves, is this interpretation a model of incidence geometry? Well, if we specify 2 points on the sphere, like the North Pole and the South Pole, we see that there's an infinite number of great circles that pass through the North Pole and the South Pole. So that would violate incidence axiom 1, which says there'd be a unique line incident with 2 points, 2 distinct points. So is this the model? No. Incidence axiom 1 fails to hold because infinitely many lines or great circles pass through, for example, the North and South Poles. Our next example is just like the 3-point geometry, but now we have a 4-point geometry. Consider the set of letters A, B, C, D. The points are the letters A, B, C, and D. And the lines, again, are subsets containing exactly 2 letters. So in this case, there are 6 lines in this geometry. Incidence, again, is set membership. So for example, point A is on line containing A and B, and so on. So we could check the 3 axioms to see if this interpretation is a model of incidence geometry, just like we checked them for the 3-point geometry. And then we could also ask ourselves, which parallel property holds? Now we can see that when we have more lines, there actually are lines that are parallel. For example, the line containing AB is parallel to the line containing CD, because they have no points incident with each other. So there are parallel lines in this geometry. So we see that it's not an elliptic parallel property, but you can investigate to see which parallel property holds in this geometry. Next, we'll look at another example of finite geometry with only finitely many points. Let's add another point. Now we have a 5-point geometry. Again, we have points A, B, C, D, and E, and the subsets containing exactly 2 letters are going to be our lines. So now there's going to be 10 subsets. And incidence is defined again as set membership. So we can ask similar questions. Is this interpretation a model of incidence geometry? So do the 3 axioms hold? And we can also look to see which parallel property holds. The 3 examples of finite geometry, the 3-point, 4-point, and 5-point geometry, those are all models of incidence geometry, and they have 3 different parallel properties. So these finite geometry examples have different parallel properties. So they have an essentially different structure, even though these are all models of incidence geometry. So when we look at models of an axiom system, sometimes 2 interpretations and 2 models could be essentially the same model with just a different description. So when 2 models are essentially the same, we say they're isomorphic. So we'll describe that in a few minutes, what it means to be isomorphic, essentially the same. So these 3 different examples show us that there's many different models of the incidence axioms. So this is good to have several models for a system because we can prove the independence of statements from given axioms using these different models. Because we know that theorems that are proved from the axioms of a system are automatically correct statements within any of the models. So if we have different models, we can have better tests to see if our statements are actually theorems. So let's talk about what it means for two models to be essentially the same thing. We say that two models of an axiom system are isomorphic if there exists a one-to-one correspondence, and this correspondence is called an isomorphism. If there exists a one-to-one correspondence between the basic objects of the system that preserves all of the basic relations of the system. So with our examples of incidence geometry, two models would be isomorphic if there's a one-to-one correspondence between the points, so P and P prime of the two models, and a one-to-one correspondence between the lines L and L prime of the two models, such that if P lies on line L, if and only if P prime lies on L prime. So this isomorphism would preserve all of the incidence relations, all the basic relations of these models. So the isomorphism translates one model to the other in such a way that it preserves all of the incidence relations. Let's look at a few definitions. We say that an axiom system is called complete if there are no independent statements. So in other words, every statement in the language of the system can either be proved or disproved from the axioms. We see that the axioms of incidence geometry are incomplete because we have some statements that are true in one model and not in others. Another definition is consistent. We say that an axiom system is consistent if it is impossible to deduce a contradiction from the axioms. So another example of a use of models is that models provide evidence for the consistency of an axiom system. So for example, if incidence geometry were inconsistent, then the supposed proof of a contradiction could be translated into a proof of a contradiction for the very simplistic model, the three-point geometry model. And the next definition is categorical. An axiom system is called categorical if all models for the system are isomorphic. The advantage of categorical axioms is that they completely describe all properties of the model that are expressible in the language of the system. So from our 3-point, 4-point, and 5-point models of incidence geometry, we see that these models are not isomorphic. They don't even have the same number of points. So we can conclude that the incidence axioms are not categorical.